Hello everybody, my name is Zach Smerge and today I'll be presenting to you rapid object detection featuring the Viola-Jones method. I'm doing this for my image processing and computer vision project here at the University of Florida. So object detection is a growing field. It's got numerous uses such as face detection and also perhaps for autonomous vehicles identifying traffic signs. The key goals today are the speed and the accuracy at which it can detect objects. Viola-Jones proposed a novel approach that not only went after accuracy but the speed at which it could identify objects. They were one of the first to achieve real-time face detection at almost 15 frames per second, and this was without the use of image differencing or skin color detection. And even at these high speeds, their detection rates are competitive with some of the best methods available today. Alright, now let's examine the four key features of the Viola-Jones detector. The first is to convert the pixel intensity values of any image into what is called an integral image. This is essentially just a summed area table. What it allows us to do is a lot of computations in a very small amount of time, and we'll see more details on this later. The next thing it uses is HAR-like features. These are common features that have been used before. They're simply different rectangular images. They achieve just above random accuracy, and they're mainly used for their simplicity and quick computation time. The third thing is the AdaBoost learning algorithm. This stands for adaptive boosting, and this is essentially the training algorithm that goes through and selects the best features out of the enormous overcomplete set of features available, and that creates what is called a strong classifier. And the final step is the cascade filter. This essentially discards all the negative subwindows as early as possible to reduce on the overall computational time and really focus more on the possible positive windows. Now let's take a detailed look at the integral image. So like I said before, this is just a summed area table in which every block is the summation of the previous blocks above it. So what this means essentially is that given the point of origin in this upper left-hand corner here, the previous blocks are defined as any blocks above it and to the left of it. So if we're looking at point A, since it's the origin point, it'll just be itself. Point B will be itself and those above it, which is A. Point C will be itself and those above it, which is A and C. And for D, that would mean A, B, C, and D are all part of it. And so the purpose of this is that it allows quick computations of any area in an image with only 4 memory lookups and 3 addition subtraction operations. And so this really produces 2 equations. The first equation is to create the integral image for a given image. And so we can see here that it's the summation of pixel D plus the summation of C plus the summation of D minus the summation of A. And we'll do an example of these in just a second. The second equation is for the area of any block at xy. And so this works backwards, and it's essentially the summation of D minus the summation of C minus the summation of D plus the summation of A. And this will make more sense when we look at some examples. And so let's first start by creating the integral image given the pixel intensity values. So you can see on the left here we have the given image and the intensities of each pixel, and then we have the resulting summed area table or integral image. So for example, if we wanted to calculate the integral image at this first red block here, it would be the summation of itself plus those above it to the left and subtracting from the corner here. And so it's the origin point, so it's just itself. The purple block is the summation of itself plus the previous sum taken from the already calculated integral table here. So that's 3 plus 5 gets us 8. And it's very similar for the blue one. If we look at the green one, this is the more practical example of what most of them are like. it's essentially its own value plus the previous summations above and to the left of it, which are 8 and 7, and then it subtracts the corner case. The reason it does this is, if you think about it, this value in purple here is this rectangular summation, and then when you add in the blue, it gets this rectangular summation, and you see that this corner point is overlapped and added twice, and so we subtract it back out to remove it the second time. And so this gets us the area of this entire square. Now, once we have the integral image and we want to calculate the area of any rectangular block in the image, it becomes very easy. So for example, say we wanted to calculate the area of the 2x2 window within this 4x4 image. The formula, as stated before, is simply D minus C minus B plus A, 4 memory lookups and 3 operations. So if we look here, at point D we have 64 minus C and minus B, that's 32 and 32, and then we add on the 16. And once again, what's happening here is D is the entire area. Oops. D is the entire area. When you subtract C, you're subtracting this block here. And then when you subtract B, you're subtracting this block here. And you can see that A is subtracted twice, so we add it back in to make up for that. We can see the result we've calculated now using the integral image is 16. If you want to check this by hand, we can look back to our original image here and see that the bottom 4 are 5, 2, 3, and 6 right here in the original. When we add those up, we also get 16, so we can see that the areas match exactly. So the next part is the features. Viola-Jones chose to use Haar-like features mainly for their simplicity and that they can be calculated very easily and with a small computational cost. They perform just above random in terms of accuracy. Essentially all they are is difference calculations. So if we were to look at this first example here, they would merely sum the area in white and then sum the area in black and return the difference between the two. Now there's numerous Haar-like features available to choose from, and this is just a small sample of those available. For my implementation, I chose to use 5 of the more basic features. You can see here 2 edge features, 2 line features, and the 4 rectangular feature. Based on the integral image we just talked about, we can see that the edge features can be done with only 6 memory lookups. If you look here at all the points, so the bottom right point, the bottom left point, the 2 middle points, and then the top right and top left points. Similarly, with the same logic, the line features can be computed with 8 memory lookups, and the 4 rectangular features can be computed with only 9 memory lookups. And so all these methods were programmed with adjustable height and width dimensions so that they could be scaled to any image size and any sub-window size, as we'll see later on. We can look at a quick example of how we would calculate the Haar features based on the integral image we talked about earlier. So for the 2 rectangle features, like I said, there's 6 points, 6 memory lookups, A, B, C, D, E, and F. And at any point, to find this difference equation, we would take the value at A minus 2 times the value of B plus the value of C minus the value of D plus 2 times the value of E and minus F. And so if this doesn't make too much sense to you, you can think about the 2 rectangles individually. So A minus D minus B plus E, likewise B minus E minus C plus F, and then when you invert the second one, you get this equation. The same thing happens here for the 3 and the 4 rectangle, and you can see the respective equations for each of them. And so they'll take 6, 8, and 9 memory lookups, and then a number of shift and add and subtract operations for each one. And it's worth noting that some of the reasons I picked these 5 features were because the 45-degree rotations for these similar features would have been much more complex. The third step is the AdaBoost learning algorithm, which stands for adaptive boosting. This is essentially a learning algorithm that is used to train the classifier and select the best subset of features out of the massive over complete set. This is a very aggressive approach. It'll disregard the majority of the hundreds of thousands of features and leave a small amount, maybe a couple hundred. And what it will produce is a weak classifier H, which consists of the feature it belongs to, a threshold value, and polarity. The way it finds this is through a repetitive algorithm where it assigns a weight to each image. Well, I should start by saying that it's fed in a set of positive negative training samples, and what it does is it repeatedly adjusts the weight for each feature based on whether it correctly or incorrectly classified the sample on the previous round. And so this will repeat itself numerous times until it comes up with the best features available. And so in my implementation, I chose to do a simpler and quicker method for training the classifiers, mainly due to timing constraints. The major differences here is that I only trained on a small number of positive images, and I pretty much set the threshold value based just on the average pixel intensities and the standard deviation of these small subset of positive images. It does have advantages in that it is much faster and easier to implement in code, and that the training period is much faster and requires less training images, no negative images, and just a couple positive images. And of course the disadvantage is the loss in accuracy and a higher rate of false positives. And you'll see that more explicitly in the sample coming up. I should also note that if you want to see the full algorithm for AdaBoost, it is listed in my paper. Finally, the last step is the cascade filter. Essentially, this is just a binary tree created with all the strong features from the AdaBoost method. And what it does is it only allows positive matches to be reevaluated. At any point, anything that registers as a negative subwindow gets immediately rejected and exits, and then the sliding subwindow moves on to the next area. And what this does is it reduces the amount of computation time spent on the false windows by immediately rejecting them. Now, the threshold values can be tuned and adjusted to allow a certain accuracy or to allow possible negative windows to progress further. And we'll see later that the lower threshold yields the higher detection rates, but it also allows for more false positives at the same time. So there's a trade-off to be made there. So for my programming, I took a little snippet of the effects of the cascade filter I wanted to show here. The example shows that less and less subwindows progress basically through each stage. So we can see in the very beginning it rejects a large amount, and it continues to reject less and less as it dwindles away the negative subwindows, and it leaves only the best subwindows to be fully evaluated. So this was done, I should say, on a 40-stage filter with a relatively low rejection threshold of only 20%, meaning if it passed 20% of the way, then it would be allowed to progress. This number could be upped a lot more, and you'd see an even greater drop-off here in the beginning, and less that make it to the full 40 stages. And so this is very beneficial because it shows you over half of the subwindows get rejected very early on and don't proceed to do all 40 stages of work. Now that we have a good understanding of how the Viola-Jones method works, let's take a look at how it performs. So they did their tests using the MIT CMU tests. These contained 130 images with 507 faces in them. It was tested on a 700 megahertz Pentium 3 processor. At their peak rate, they were able to achieve 0.06 seconds per image, which is a very robust, almost 15 frames per second, We should mention that this was on a 384 by 288 grayscale image that started at a scaling rate of 1.25 and a step size of 1.5. This is, I should reiterate, the optimal scenario. In terms of accuracy, we can look here and see that comparing the Viola-Jones to two of the other top algorithms show that the accuracy is very comparable. There's also a trade-off that you can see here between the false positive rate and the accuracy. So the more false positives we allow, the higher the detection accuracy we're going to get. And likewise, if we want very few false positives, that accuracy rate dwindles. And so depending on where we're at on that scale, you can see the Viola-Jones performs just above or just below these other two methods. So these next couple slides show us the typical outputs for the Viola-Jones method. What we can see here are 4 different inspections of the same image using different cascade stages, so 16, 21, 26, and 31 stages respectively. And we can see, as we said before, that as the number of stage increases, we get significantly less false positives. The other takeaway from these, looking at them, is the number of times that the same face is detected. And so you can see that across all these images, the girl's same face is detected many, many times. So here's a typical output from my experimentation. You can see that due to the use of the less accurate predictor and using less HAR features and essentially less amounts of features total, the accuracy is significantly degraded, but you still get the same idea as the Viola-Jones method. And so you can see that in some of these stop sign is detected, others it's false positive. And we can vary these settings, as I'll show you in a couple seconds. Varying these settings shows dramatically different results. Alrighty, now I'd like to show you a little behind the scenes work with my coding. As you can see here, there's a main file where it does most of the scanning. There's 4 separate files here going on. There's the HAR features, which contains essentially just the HAR features. Another one for calculating the integral image. A test file that you can disregard, it's just old files or debug stuff. And then there's the training file, where it actually calls the integral image and HAR features functions and creates the cascade filter and whatnot. So what I want to show you here is just the level of flexibility that is going on here, so that we can test different configurations and really get a feel for what's going on. You'll see there's a number of defined statements in the main as well as in training that can alter the way our algorithm is functioning. So the first thing we can see here is that we have 50 strong features, essentially a 50-stage cascade, each one with 10 weak features in it. We also have a division factor here that controls essentially how many features are available, and so right now we're using almost 5,000 features per subwindow. Like I said, everything here is coded to be a little bit smaller and more manageable compared to the full Viola-Jones method. You can see here our cascade filter is set to 20% accuracy to pass, which is a little bit low, and we have a number of other things here. These first couple have to deal with the size of the scanning window and essentially how big the dimensions, how big it is, and how far it shifts each iteration. And so I'm just going to run this so you can get an idea of how it works. And right now it takes a little bit longer due to the number of outputs. It outputs a lot of debug information to files, as well as writing all these images. And so you can see here, this is the traffic sign test on the stop signs. We get a few hits in a couple of these. Due to the scanning window size, it's a little too big for these smaller ones here, and there's a lot of false positives as well in all of these. Now we can go in here and we can change, and we can get rid of say the cascade filter if you want, and make this 0, and we can see without the cascade filter that's going to take much longer because it has to go through every single one now. So this should just give you a little idea. So what it's doing right now is it's going through and it's training itself based on the positive examples, and then going through each one iteratively. I suspect this will also create more false positives. Yeah, it did create a couple more false positives in some of these. So that just kind of gives you an idea of what's going on behind the scenes. So in conclusion, the Viola-Jones method we have just explored is one of the fastest tools for object detections, and it has competitive accuracy and false positive rates. So it's based around these 4 primary features. Once again, the use of the integral image for quick computations, the simple Har-like features used for classification, the adaptive boosting algorithm used to create strong features from the host of classifiers, and the use of a cascade filter to reject the massive amounts of negative subwindows and reduce the overall number of computations done. So I'd like to now talk about a couple future improvements that I think could be worth the research. The first is to take advantage of the reused features. So if you look through here, you'll see that most of the features are recalculated multiple times due to the overlapping of the search window. So as this window slides along, essentially what is in the upper right hand corner of one window will be in the middle of the next window, and it'll get calculated multiple times. So I believe that if we were to restructure the algorithm to scan by feature rather than scanning by subwindow, we may be able to reuse these features and calculate them only one time. And this, I think, would greatly reduce the number of computations done overall. I think the second improvement is a little more intuitive, and this is to reduce the multiple detections of the same object as we saw previously. So anytime there's a positive window, due to the way the scanning method shifts through the image, it will detect the same face or the same object multiple times, very close to one another and at different window sizes. So I think an easy fix for this would be to scan starting with the largest subwindow first, and then once a face is found inside that subwindow, to automatically reject any subwindows within that positive match. And so this would greatly reduce the overall computations, because the majority of the subwindows that make it through the entire cascade filter are repetitive positive matches. So this would take out a bulk of the computations done overall. And here's a list of some of the most important references for anyone that's interested. And I'd just like to thank you once again for watching my video.